Hello everyone, my name is Xiang Pan from Google. Today I will present our paper, FlowCog. This paper was started when I was in Northwestern University, and it was joint work also by Johns Hopkins University and Zhejiang University. First, I will start a motivating example, and I will use this example throughout my entire presentation. So this is a weather app. And in its setting activity, there is a checkbox asking if user would like to share the location, so this app can always choose the city for the user. When this app is started, user's location as well as a reference to this checkbox are stored in the main activity. When user clicks the update weather button in the main activity, then its callback, perform update weather, will be invoked. And this function, in this function, user's location as well as the value of this always sharing location checkbox will be used to create a new update weather task. Once this task is executed, its callback doing background will be invoked, and in this callback, it will first check if user has selected this always sharing location checkbox. If yes, then that will send the data through the post data. Send the user's location through the post data static method, and then in this method, it will prepare a weather update request and send to the server through HTTP client. If user does not select always sharing user location checkbox, then this app will pop up the dialog asking if user would like to share location for this time only. Okay, if user click the agree and its unclick event listener will be invoked, and then user's location will still be sent out to the server. If user click disagree, user location will not be sent out to the server. Okay, so apparently there is a data flow here. The source of the data flow is the user's location. It goes all the way from the main activity to the update weather task, and then to the post data static function, and finally to the HTTP client, which is the sink of the flow. How to detect such data flow? This problem has been studied extensively. The system listed here, like FlowDroid or TenDroid, that can find all such data flows either statically or dynamically. And this list is far from complete. But the problem is, not all such flows are bad. In our motivating example, the flow of sharing user's location to the server, which is legitimate because the app has told the user what's the flow's behavior. So based on our observation, we manually checked like more than 2,000 data flows. We found more than half of them are legitimate. So this is a big limitation shared by all existing systems, because they cannot tell which flow is legitimate and which is not. Considering the fact that the users of such system always need to take care of a large number of apps, then this would incur a big burden for those users. For example, one of the target users for such system would be app market. App markets, they want to detect real privacy leakage on the apps on their market. So because of this limitation, they need to verify each flow's legitimacy, which is super expensive and sometimes it's even not possible. So we really need a system that can automatically determine each flow's legitimacy. Okay, then we have FlowCog. FlowCog takes a big step over existing app analysis system. It's the first system that can extract flow-specific semantics, and then it uses NLP, natural language processing technique, to associate the semantic with the flow's behavior. Then, based on if the semantic provides some information of this behavior, we would say this flow is legitimate. Otherwise, it's not. Here's some high-level steps of how it works. First, it will associate each flow with the related views through static analysis and an optional dynamic analysis. So the first question is, what's related view? Related view refers to the UI views that can somehow change the data flow's execution. In our motivating example, the update weather button and the always sharing location checkbox and the dialog that asking if users want to share location, these three are all the views that's related to this flow. Then we want to extract the text and image from each view, which we refer to these views as semantics. Next, with this semantics, we will determine if that provides sufficient information about this flow's behavior. If yes, then this flow is good. Otherwise, it's malicious. Okay, now let's see the architecture of FlowCog. First, for an app, we will run data flow analysis using FlowDroid. After FlowDroid extracts all the data flows, for each flow, we will extract its activation events and guarding conditions through static analysis. We have formal definition of activation event and guarding conditions in the paper. Intuitively, activation event is a callback function that can initiate or complete data flow. And the guarding conditions are the conditional statements that one of these branch might lead to the sync of this data flow, and the other branch might not. So in our motivating example, the unclick event listener of the update weather and the unclick event listener of the agree button in the alert dialog are both activation events. Also, the doing background callback function of the update weather task is also activation event. As for guarding condition, the if statements are checked if user has selected always sharing location checkbox is a guarding condition. We need to find this for because that can somehow change the execution of the data flow. Okay, then we send the activation events and the guarding conditions as well as this flows path to a component called View Dependency Explorer. This component will run tagged analysis to find the related views of this flow. So, for example, the update weather button and the always sharing location checkbox, etc. These steps it requires some value analysis. So we have an optional component called dynamic analysis component that could give some help. Then after this step is done, we got all the related views. Then we send these views to the Semantic Extractor. This one will extract the text and images from this view. For example, from the always sharing location checkbox, we can extract the following text, like share location to automatically update city as this view's semantics. If the semantic is the image, we also need to convert them to a text through OCR technique and Google image technique. Okay, so semantic extractor's output is a flow-specific text. Then, together with app description, we will send them to an NLP, natural language processing module. This module that can convert the text into verb-noun pairs. For example, the sentence "share location to automatically update city" will be converted to "update city, share location." The reason we want to do this is because we first want to remove those useless words. Then we want to still preserve the most information of the text. Next, we will go through the filter. The filter will further remove those less informative words like Android or app, something like that. And then it will normalize all the text. The result will be sent to the classifier. The classifier is composed of two subclassifiers. One is learning classifier, the other is learning free classifier. Learning classifier can always achieve the best results given sufficient data. But the problem is, in our data set, some types of flow don't have sufficient training data. So a learning free classifier is necessary here because those flows perform really bad on the learning-based classifier. So the results of these two classifiers will be sent to a logistic regression and then give a binary result, whether this flow is legitimate or not. Okay. Now let's see some design details. First, we want to know how to find the flows related views. Actually, this problem can be formalized into a tent analysis problem. Source, of course, is all the views. Views can be declared statically in a layout file and referenced through a find view by ID statement. In that case, we need to put all the find view by ID call as a source in the source list. Also, views could be created programmatically. So all the new view and new dialog statements should be included in the source also. As for the sink, there are three types of sinks depending on how the view is related to the flow. First, a view could change the flow's path directly. So all the statements in a given data flow should be included in the sink list. And also, a view could change the guarding conditions value. In our motivating example, the always shared location checkbox belongs to such case. So we need to add all the guarding conditions in the sink list. And also, another case is the flow's activation events could be registered on the view. So like in our motivating example, the update weather button and the dialog asking user for location service belong to such cases. So we need to add all the activation events registration statements in the sink. After we get all the source and sink, we will run tent analysis. We use the FDS framework provided by FlowJoy. Let's see how the classifier works. We already know that flow-specific text and app description will go through the NLP module and the field module and finally arrive at the classifier. And for learning classifier, we first use TF-IDF to vectorize the input, and then classify using SVM and gradient boosting. The reason we choose a combination of these two algorithms because it works best among all we have tried. You can refer to the paper for details. We tried like 5 different algorithms. And for the learning free classifier, we use work2vec module to convert 2 inputs into 2 vector lists and then compare their similarity scores. So one input we know is app description and the flow specific text. We want this input to represent this flow's semantics. The other input is a documentation of the source and sink method. We want this input to represent this flow's behavior. So intuitively, if the semantics can somehow describe this flow's behavior, then we would expect the similarity score between these 2 inputs would be high. Note that the work2vec module still needs to be trained, but it can be trained using just a general corpus like Wikipedia. So that's why this classifier still works for the flows with a small data set. And the results of these 2 classifiers will be sent to the logistic regression and get a binary results indicating whether this flow is legitimate or not. Okay, let's briefly talk about the implementation. The whole system of FlowCog is implemented in Java and Python in about 16,000 lines of code. The major part is how to extract the flow-related semantics. This part is implemented in 12,000 lines of code, Java code. Our system is using the time analysis framework provided by FlowJoy. We recently noticed that FlowJoy, the FlowJoy framework has evolved to version 2, and that works much more efficiently than existing ones. So we are actually actively migrate to that version. And the classifier is written in Python in about 3,000 lines of code. And dynamic analysis, I didn't talk too much about this in the presentation, but basically we use a suite to rewrite the app. And then we use our own fuzzing tool called Apps Playground to explore the app. So it's finished. It's implemented in about 1,000 lines of Python and Java code. So evaluation. First, ground truth. We run FlowJoy on 4,500 benign apps from Google Play and 1,500 malicious apps from JBean dataset. And we set the data flows timeout at 20 minutes per app. Roughly 1/3 of the apps finished, and we got 200 of apps got 2,342 flows. Among these 2,000 flows, we manually label each flow to determine their legitimacy. And the results show that about 1,363 legitimate flows, and the rest 979 malicious flows. So based on this ground truth, we run FlowCog to see its accuracy. It turns out FlowCog can achieve a high accuracy. The overall accuracy will be 90.2% with the precision I recall as 90.1% and 93.1% respectively. And the accuracy for benign and malicious apps are similar, 90.7% versus 89.6%. We further break down the accuracy based on the type of source and sink. It turns out there is a big difference. For example, the flows with the credential that can achieve a high accuracy, 96%, but the flow with the calendar, the accuracy is low, 66%. After some analysis, we found the root reason should be the size of the data. So, for example, in this chart, the x-axis is the number of flows. The y-axis is the accuracy. So you can see roughly with the number of flows increase, the accuracy increase. So then it's safe to say that less accurate flow types can still be improved given more training data. Let's see some case study. This is an app called Home of Ocarina. It's an official app of a company called Home of Ocarina. It has a data flow that will look up user's location for map service, but the app's description said nothing about this. Okay, so FlowCog can find this car icon button is related to this flow, and then it can further extract the semantics from this field, which, when translated into English, is the map and the location of Home of Ocarina. So then FlowCog label this flow as legitimate. I'll skip this one for time reason. And the other one is the Merry Christmas. This is a gaming app. It will allow you to play a very stupid game. But as a background, it will send out all the users' private information to a server, like the phone number, contacts, location, etc. And FlowCog tried to extract the semantics of these flows actually, and found all the semantics just gaming tips, like move this block to the target empty position, etc. None of them are related to the flow's behavior. So that's why this flow is labeled as malicious. So conclusion. So FlowCog is the first system that can extract flow-specific semantics. And FlowCog adopts an NLP technique to correlate the flow-specific semantics with flow's behavior to determine flow's legitimacy. And our evaluation show FlowCog can achieve a high accuracy, like 90.1% precision and 93% recall. Thanks. Our system is open source.
All right, are there any questions? All right, so I actually have a question. When you are gathering the semantic information, you say you pull in the documentation. Are you just pulling this from like the Android documentation?
Yeah,
okay.
Just Android. We want that to show, like, to represent flow's behavior.
Okay, all right.
Mm-hmm. But that's only for learning free-based. We also have learning-based that's done near this. For learning free-based, we don't have any learning part. So we need a way to compare like flow's semantic and flow's behavior. Yeah. That's the flow behavior.
Any other questions?
Hi, very nice work. So my question has to do with the interactivity of the flow. So in some cases, you use the user interface to track or to see where the flow starts. Did you find any correlation between maybe benign flows that come from the user pressing a button and malicious flows that they are just started because the app starts the flows themselves? Or
so your question is there's benign flow. Benign flow means the flow started by user?
Yeah, I mean, if you could make somehow that correlation or not, or basically if the malicious flows are started by the apps without user interaction.
Okay, actually it has nothing about the user interaction. It has something about user interaction, but that's not a determining factor. The determining factor is whether the semantics provides sufficient information about this flow's behavior. For example, if user click a button to start a flow, but the flow tells you like, I want to just play this game, but actually it send out to your phone numbers to somewhere else. That's malicious. We can detect that. We actually detected that.
Okay, thank you.
Thank you.
All right, let's go ahead and thank the speaker one more time.